Do you see the screen now?
Yes, doctor.
Okay. So we were talking about how to get the expression of the friction factor for laminar case. All you have to do is to replace HF by its expression, which is calculated based on the analytical solution for the velocity profile. So if I replace here, I get 32 times mu times L times V bar over rho GD square times 2GD over V bar square times L. So you can simplify. You have G, G, D, D, okay. You have 64 mu V bar and V bar here. So 64 mu over rho V bar D. And as you can see, this is the opposite of Reynolds number. So in case of laminar flow in a duct, you can say that the friction factor can be computed by doing 64 over Reynolds number, which is a very simple result, okay? So just I should know the Reynolds number, and it's expected that larger the Reynolds, lower the friction factor. You know why? Because in this case, the viscous effect will not be dominant, and the friction is mainly due to viscous effects, okay? Because H is proportional to mu, the viscosity. And as inertia forces increase compared to viscous forces, the F decreases, okay? Now, the challenge is, what if Reynolds is larger? What do we do in case of turbulent flows? We don't have an analytical solution. We should think about other methods. So the first difference between laminar and turbulent is that you can visually see and distinguish a laminar from a turbulent flow, because in laminar you have smooth streamlines, while in turbulent flow you have a lot of mixings and curls inside in your flow. Now, the second difference is in the velocity time trace and the presence of fluctuations. In case of stud in laminar, your velocity, your average velocity, okay, in case it's a, let's say, if in case you have a steady application and V, let's say V average is constant, then V, if you look at, if you measure your velocity at a certain point, it will not vary if you have a steady state application. At one location, the velocity will remain the same. In case of turbulent flow, it will do some oscillations around the average value, because you have source of turbulence. Turbulence will lead to fluctuations of velocity around a certain average value. This will make analysis much more complex, okay? So we have then to account for turbulence effect, which is really complex to solve, and we cannot find it analytically, so we should go to experiments or computational fluid dynamics. And as the Reynolds number increase, the mixing behavior increase, and the turbulence level will increase. This is why, to deal with this, okay, we define then from experiments for which Reynolds numbers we have laminar flow, for which Reynolds numbers we have turbulent. Now, any fluid in a pipe, okay, had to enter the pipe at some location. The region of flow near where the fluid enters the pipe is termed the entrance region and is illustrated in the figure. It may be the first few feet of a pipe connected to a tank or the initial portion for a long run of hot air duct coming from a furnace. Now, the shape of the velocity profile in the pipe will depend on whether the flow is laminar or turbulent, as does the length of the entrance region. As with many other properties of pipe flow, the dimensionless entrance length correlates quite well with the Reynolds number. What do we mean by this? What is the entrance length? Look, let me illustrate, let me show you a figure, okay? Look, if you consider, for example, a laminar flow, but in general, for laminar flow, you can have a certain analytical solution, okay? But of course, and we say once your flow is fully developed, but before your flow is fully developed, you have a transient behavior. Because look, if you have a reservoir and you want to have the flow coming from the reservoir through the ducting system, at the entrance first, you have a uniform profile of velocity. But as your flow will enter the pipe, it will be subjected to viscous effects. So the profile, the uniform profile will gradually change. Okay? So you have what we call development of a boundary layer. Within the boundary layer, the viscous effects are dominant. Okay? So as you can see, you will have a change in velocity, a sudden change in velocity within your boundary layer, while in the inviscid core region, we call it inviscid because it's not affected by viscous effects, you have nearly a uniform profile. But as you enter your pipe, as you move with a certain length, you will not have any inviscid part anymore. So just you need a certain entrance region to have complete development of your boundary layer. So as you can see here, you have a boundary layer at the wall from this side and a boundary at the wall from this side. So when they meet, when the two boundary layers will meet, then the inviscid core region will end up, and you don't. The transient region then is done. Okay. So this region where you have development of boundary layers and you have the presence of an inviscid core is called entrance region. In this course, we will not deal with it. This is a complex, very complex region where you have a lot of variation and will not study it. We'll study fully developed flow. When we say fully developed, this means that the profile is established and it's not varying anymore. Okay, unless we have some a change here. For example, if you have a 180 degrees turn, this will induce a modification. So this will also need a certain this will include a transient behavior, and it will require again a new developing flow to be able to reach again a fully developed. Okay, now in this course we'll just, in case of laminar flows, we'll just do analysis of fully developed flow. And even if we deal with turbulent flow, we'll not consider effect of entrance regions. But of course, in a turbulent flow, the entrance region will be much smaller. You know why? Because the viscous effects will be reduced in turbulent flows, since inertia forces are dominant. So you will not have a very large entrance region. We'll see this in a figure in a while. You will have in a very fast way establishment of the profile. Aslan, for turbulent flow, more your flow is turbulent, then your profile is nearly uniform. لأنه viscous effects will not have a large effect on the flow. So بس حيأثروا على very small part وبالباقي دغري بيكون uniform nearly. This is why larger is Reynolds, we are closer to the uniform profile, because viscous effects هن اللي بيخلوا velocity profile to vary. هن اللي بيخلقوا gradient and velocity. If viscous effects are not dominant, this behavior will not be seen. Okay, so if you look, for example, we'll see a figure for turbulent flow in future slides. Okay, but what you should know is that this entrance region, which is a transient region, is not is depending if the flow is laminar or turbulent. So L entrance over D is 0.06 Reynolds for laminar flow, while it is 4.4 Reynolds to the power 1 over 6 for turbulent flow. And you can check that the length of entrance is much smaller in case of turbulent flows. Okay, so now, this graph shows you how the entrance region, in the entrance region, you have variation of properties, because if you remember when we talked about fully developed flow for laminar cases, we demonstrated together that in the region of fully developed flow, the pressure gradient is constant. While for the entrance region, if you measure the pressure variation and you draw it, you will not have a linear variation of pressure. It's not a constant pressure gradient, because this zone, okay, in this zone you are moving towards the fully developed. So as you can see, you have the pressure drop is larger. أول ما نفوت بيكون أعلى drop، أعلى gradient. And as we move through the duct بيخف هالإفكت until reaching the constant pressure gradient slope بال fully developed region. Okay. هلا don't worry a lot about entrance regions. يعني we will mainly focus on fully developed regions. Now look, here you compare profiles in laminar and turbulent. You can see clearly that in turbulent profile you are much more closer to the uniform profile. كل ما زاد الرينولد كل ما قربنا على uniform profile, because as we said, the effect of viscous forces will be reduced. Now, whenever you have turbulent flow, you should perform experiments, okay? Because no analytical solution is present. Here, for example, we try to measure the pressure drop for different velocities, and we have observed that in case of laminar flow, the pressure drop value is linear with V, while when we move to the turbulent region, the slope of variation of pressure drop with V is much larger. So this indicates already a variation in behavior. And this is how they could detect, if you want, the value of Reynolds. And here, from this point, you can say that for this point, the Reynolds number will correspond to transition. Because for smaller Reynolds, you have laminar behavior. And after this Reynolds number, you have a transition period. So we call it transition between laminar and turbulent. And finally, you can reach a certain profile where your pressure drop is proportional in the turbulent flow region. We demonstrated that experimentally from fitting techniques, that the pressure drop is proportional to V to the power 1.75. So the pressure drop in turbulent flow will increase in a much faster way in case of turbulent flows than in case of laminar flow. And from here, okay, we can say that in case of turbulent flows, we should perform the experiment to be able to derive to come up with values for friction. Okay. So as we said, no analytical solution is possible for turbulent flow. Then we should try to experimentally find how the velocity profile is, and how is if you want then the shear stress, because the shear is depending on velocity profile. So the technique will be to measure experimentally velocities, to do fitting techniques to find an equation for the profile of velocity, and from the profile of velocity equation to get the value of the shear stress. Okay, so this is the technique that we will follow in the next step. So until now we have seen that in case of laminar flow in a circular duct, we have a parabolic profile in case of laminar case, while in case of turbulent, the profile is closer to uniform profile. And as Reynolds increase, we are closer to the uniform one. While for in the transient regions, it is between the parabolic and the uniform profile. Okay, now what is the technique to use? So here we started to think about what should be the experiments performed in order to know the behavior of turbulent flows. فصاروا يقولوا شو هن البارامترز that are important؟ صاروا يقولوا مثل chapter 7، يعني هون عم نعمل chapter 7 exactly. Parameters that are important are the velocity of the flow field. بمجرد ما يكون في flow field يعني في rho وميو. Okay. What also we have the here shear is important for us. Okay. We have friction factors also is important. So we can define tau. We can define the friction factor F. And we said what we want to do is to try to find an expression. Our purpose as a first stage is to find u function of y. Okay. And to find u function of y, we should develop dimensionless numbers related to u and related to y. Okay. So first we said, what can be the dimensionless number that is related to u? If we do the analysis here between these parameters, okay, you have the friction factor who already dimensionless number related to HF. So friction factor جبناه من HF. Now to define a velocity parameters that is without dimension، إذا بنطلع بهول variables we can demonstrate، بدي إياكم تعملوا لها practice من chapter 7. You can demonstrate إنه it can be related to the shear and to the density of your flow. And we can define first what we call a friction velocity, u star, which is tau over rho to the power 1 over 2. This, so that you can say that u over u star is a dimensionless number. So this is your first group. Your first group is u over tau over rho to the power 1/2. You can try to do it using chapter 7 from the pi group analysis or from the inspection method. احنا طلعنا 2 methods to get a group. You can find that your first group is u over u star. Since you need to relate u function of y, مثل ما لقينا parameter, if you want dimensionless parameter related to velocity, بدنا نلاقي dimensionless parameter related to y. وإذا بنطلع بالبارامترز تبعنا اللي هن رو وميو y, أكيد y is a variable here. It's important because we are interested in the variation of velocity with y. Then you can form the following group: y times u star over mu. هيدي الميو اسمها kinematic viscosity. هي related للديناميك viscosity through the following. It's mu over rho. يعني انتو إذا بتطلعوا بالparameters you will be able to relate y. Okay. You will be able to relate first y dimension هي L. Okay. Dimension of y هي L. So the group of y هو y over n. هلا وقت عملنا analysis ل لهول ال لهول الجروبس اوكي يلي هن سوري صارت 3. طيب انا كنت وعدتكم to stop at 3. اوكي look we'll continue this idea بس بدي اياكم to try just to try for next time okay to find the groups involved here using chapter 7. هيدا practice on chapter 7 know how we can define dimensionless numbers okay related to and form a chart إذا بدكم مثل ما حكينا أنا وياكم قبل to experimentally use the result to be extrapolated to general case. So we'll continue this idea next time. Okay حنتفق على session online session to be able to finish before Monday. Okay ساعتها Monday will be our last session. So بركي نعمل on Friday or Saturday as it's convenient for you. هلا we discuss on the group. Okay يلا we'll stop here. Thank you.